So our next speaker is Pierluigi Vallarino from Erasmus University in Rotterdam. This is a joint work as far as you have shown with Mirko Rubin and Federico Carlini, and it is called New Rank-Based Tests and Estimators for Common Dynamic Factors. The floor is yours, Pierluigi.
Thank you very much, Alessandra. So yeah, this paper, New Rank-Based Tests and Estimators for Common Dynamic Factors, is joint work with Federico Carlini and Mirko Rubin. And what we do is we test and estimate the number of common dynamic factors in large panel data. In particular, we are concerned with testing and estimating the number of common dynamic factors in dynamic factor models of this type. So we have n observed time series at time t, and the load on contemporaneous and lagged values of q common dynamic factors that we pull into the vector h at time t, for instance. These factors are hidden, and they follow a stationary VRP process, as you can read in equation q. This VRP is characterized by some innovations WT. Now, when these orders S and P are finite, so the so-called restricted dynamic factor model, we can cast equations 1 and 2 into so-called static factor representation. In particular, YT now loads only on contemporaneous values on some now static factors, FT. FT is a vector, is R-dimensional, and is obtained by stacking together contemporaneous and lagged values of the dynamic factors. So R is larger than Q, it is exactly Q times S plus 1. Essentially, the stationary VR1 for static factors is the companion form of the previous VRP. And as always, in companion form, the innovations VT take this particular form that we can read here. The first Q terms are in the innovations of the VRP, while the remaining entries are 0. Therefore, the covariance matrix of VT is necessarily singular. In particular, it has rank Q, pretty smaller than R, so that the smallest R minus Q eigenvalues are exactly 0. The largest Q1s are positive, the remaining ones are 0. Therefore, testing the number of common dynamic factors in these restricted dynamic factor models is equivalent to testing the rank of this variance-covariance matrix. And this is the approach that we pursue in this paper. Now, testing the rank of a finite dimensional positive semi-definite matrix is a non-standard problem. Indeed, usual rank tests do not apply in this case. This is because the covariance matrix of the estimator for the PSD matrix of interest is necessarily singular. For team Gagliardini and Scaillier recently developed some methodology to test the rank of a finite dimensional PSD matrix in panel data where the temporal dimension is finite, while the number of cross-sectional units is diverging. On the other hand, we develop a test for the rank of this type of matrices in large panel data, so panel data where both dimensions are jointly diverging. The test is based on the asymptotic distribution of functions of estimated eigenvalues of the covariance matrix of interest, and we propose both a plug-in and a bootstrap implementation. Now, in similar dynamic factor models, consistent estimators of Q were developed by Bayeneng and Amengual and Watson, as well as by Brighton and Piggosh. First two were based on principal component analysis. Brighton and Piggosh considered canonical correlation analysis. Differently from this paper, we don't just develop a consistent estimator, but we rather construct a fully fledged asymptotic testing procedure on top of which we can then construct a consistent estimator. Now, when P and S are not necessarily finite, that is the generalized dynamic factor model, Alain and Liska proposed a consistent estimator of Q, while Onatsky developed a test, and on top of which he developed also a consistent estimator. So in let's say, at a high level, our methodology is more similar to the approach of Onatsky. First a test, and then a consistent estimator. So this is the modeling framework, dynamic factor model with n observable time series, little r static factors F breve. F breve follows the stationary VR1, innovations are V breve. The innovations V breve are R-dimensional, they're obtained through this matrix vector product, where we have a full column rank matrix, G, and a vector eta t. Eta t is Q-dimensional and is the generic element of an IID collection of zero mean and identity covariance matrix primitive shocks. So these are the primitive shocks that we're going to look for, whose number we're going to look for in this paper. Now, when Q is smaller than R, like we said before, the smallest R minus Q eigenvalues of the covariance matrix of V will be 0. Indeed, this covariance matrix, sigma breve V, will be given by G times G prime, so that it has rank Q, which is at most R. And when the dynamic factors are strictly less than the static factors, the smallest R minus Q eigenvalues are 0. And therefore, this chain of inequalities and equalities hold. So basically, we have Q large inequalities, one strict inequality, and then all 0 eigenvalues. Now, this chain of equalities will be the generic hypothesis of interest in this paper. And it corresponds to the hypothesis that there are Q primitive shocks, or equivalently in this paper, common dynamic factors in the panel data of interest. And what we do is we select this number of primitive shocks with the following test. We consider the null hypothesis that there are Q dynamic factors against the alternative that there are more, strictly more, than Q dynamic factors. And we do it for any positive integer between 1 and little r minus 1. So the alternative is always more than Q primitive shocks. Practically, how do we proceed? Well, a first step is to use principal component analysis on the observed panel to estimate static factors with a principal component estimator We then estimate by ordinary least squares this VR1 that we can read here, and therefore obtain the OLS estimator of the variance covariance matrix of interest, the one of sigma breve V, and sum its smallest R minus Q estimated eigenvalues. So we have now this sum, psi hat Q. Psi hat Q means that we are summing the smallest R minus Q estimated eigenvalues, and intuition is if these eigenvalues in population are 0, then this empirical sum, this thing that we have estimated, should be approximately 0. So when this is approximately 0, the smallest eigenvalues that we are looking for are not statistically different from 0, and therefore there are Q dynamic factors in the data. And what we do is we perform a sequential test hypothesis using the asymptotic distribution of a test statistic that is based on this sum. Now, its base is not exactly this sum, because testing whether this sum is equal to 0 is like testing a null hypothesis where the parameter of interest is at the boundary of the parameter space. And that would pose excessive complications that we would like to avoid. And therefore, we consider a recentered and rescaled statistic. We have a convergence rate, n times square root of t. We have a scaling factor, omega u. And then we have this difference where we have the sum, psi hat, but an asymptotic bias that vanishes at rate 1 over n, and which is almost surely positive. So this difference will be supported over the entire real line. An intuition behind this test statistic is when we estimate principal components by static factors by principal component, we are committing an estimation error. Now, this estimation error is, let's say, brought forward when we estimated variance covariance matrix of interest and also its spectrum. So all the quantities that we are considering when writing the test are contaminated by an estimation error. We use a higher order asymptotic expansion based on this estimation error to construct expressions for this bias and for this variance, and then we employ central limit theorems and uniform law of large numbers to derive the asymptotic distribution of this object here. And under 7 assumptions that we have in the appendix to these slides, we can show that under the null, we converge in distribution to standard Gaussian, while under the alternative, we diverge in probability to plus infinity. And this holds jointly with respect to the sample sizes that are diverging to infinity. Of course, these quantities are based on population values, and therefore this test statistic here is unfeasible in practice. What we do is we consider another test statistic, psi tilde, where we replace the scaling and the bias term with consistent estimators. So this is now a feasible test statistic, and under 2 more assumptions, we can show that this test statistic, psi tilde, mimics the asymptotic behavior of the unfeasible test statistic of theorem 1. So we can use it to test the generic null of interest and reject HQ at a significance level alpha between 0 and 1 whenever xi tilde exceeds the 1 minus alpha quantile of a standard Gaussian. So this is a right tail test. Now we have a test, and we want to develop a consistent estimator. The idea is we can iteratively testing by starting with testing the null of one common dynamic factor against the alternative of at least two dynamic factors. And then we proceed iteratively until we can't reject the null. Of course, this is not a consistent selection procedure, estimation procedure, in that the test has an asymptotic size alpha strictly larger than 0. And so we would be estimating the true number of common dynamic factors only with probability approaching 1 minus alpha, which is strictly smaller than 1. So to control for type 1 error, we consider a sequence of probability levels indexed by n and t, such that it shrinks to 0 as the sample sizes are diverging, and then consider this estimator, q hat. Q hat is the smallest positive integer, such that we can't reject the null of q common dynamic factors based on critical values drawn as quantiles of a standard normal, but at probability level 1 minus alpha and t. So not 1 minus alpha anymore, but 1 minus alpha and t. And under the same assumptions as before, we can show that this is a consistent estimator of the number of common dynamic factors. And to improve finite sample performances of the test, we introduce a bootstrap implementation that works along the lines of that by Gonçalves and Perron. This is essentially a residual-based while bootstrap to resample observations on the panel, and we impose the null of Q dynamic factors in the bootstrap data generating process. Furthermore, we also use estimated parameters as true bootstrap parameters when resampling. We then end up with capital B bootstrap sample, say 99 bootstrap samples, and for each of them we compute a feasible test statistic, and therefore we have a distribution under the bootstrap probability measure of test statistics, and then compare the empirical test statistic with the critical value drawn from this empirical bootstrap distribution. Now I would like to present some results, Monte Carlo results. We consider a data generating process similar to that of Bayen-Eng, Amenwal-Watson, and Bratter and Pigers. So we have a dynamic factor model in static factor representation. There are 7 static factors and 5 dynamic factors. The VR is diagonal and has a variance covariance matrix whose eigenvalues are very close to 0, even when they're non-zero. So this DGP is rather tough for our test in that the threshold between non-zero and 0 eigenvalues is very blurry. Here we have empirical size and powers for the test. In the left panel, we can see the plugin implementation, the one based on theorem Q. We see that is quite oversized, especially for relatively small sample sizes. Results improve, but still the size is not good when the sample sizes are increasing. The power, though, is good, even when we consider size-adjusted power. These are size-adjusted powers, and we're considering power against the null of 4 common dynamic factors. So this is the null that is the toughest to detect for our test. We then look at results with the bootstrap implementation. We see that the size is now much better, is now much closer to nominal values. There is a very minor loss of power, which is quite expected when we run a bootstrap schema under the null. Here we have in blue histograms. Basically, blue histograms are the empirical distribution of the test statistic across the 2000 Monte Carlo sample. And we see that in the case of 100 cross-sectional units and 100 points in time, this distribution, this blue histogram, is rather shifted to the right with respect to the standard Gaussian asymptotic density. In yellow, we have the bootstrap distribution for the first Monte Carlo sample, which we see is very close to the empirical, to the simulated distribution of the test statistic. Things do improve for what regards the Monte Carlo distribution when we move to 400 cross-sectional units and 600 points in time, but still we see that there is too much mass in the right tail. Now we have a comparison with other estimators of Q. In particular, we have the average estimated number of common dynamic factors using the estimators by Bayen-Eng, Q3 and Q4, those by Amenwal and Watson, A and B.
and that by Vallarino and Pierluigi. We then have our estimator based on non-adjusted critical values, the one based on adjusted critical values, and the one based on the bootstrap. We see that in 7 out of 9 sample sizes, our estimators outperform all the other ones proposed in the literature. Estimators by Manuel and Watson perform rather well, extremely well from time to time, and that must be acknowledged. Finally, we compare ourselves with 6 possible estimators that can be constructed using the methodology of Allen and Liska. We see that in 8 out of 9 cases, our estimators outperform those of Allen and Liska. Only one instance, the ones of HL12, is outperforming our estimators. So basically, we propose new tests and estimator for the number of common dynamic factors in large panels. We showed that we can find implementations that have good finite sample properties, and we can improve upon most of excellent approaches for the considered data generating process. In the paper, we also have 5 more data generating processes, and we get similar results. We also consider 2 empirical applications in the paper. One is macrofinancial with the FredMD dataset, and one is purely financial on volatilities on S&P 500 constituents. In the paper, we also construct an alternative test and estimator based on canonical correlation analysis. Indeed, those that I presented today are more in line with Bai-Eng or, if you want, Manuel and Watson, while this one that we also have in the paper is more in line with Vallarino and Pierluigi. And finally, we also develop an estimator for the process of the Q primitive shocks, or if you want, dynamic factors. Future research will study the first order bootstrap validity of the implementation that we propose, and perhaps inference on these estimated primitive shocks, as well as considering applications to singular favor models.
Are you done, Pierluigi?
Oh, yes, I'm done.
Oh, okay. Thank you then.
Thank you very much for your attention.
Stop the recording.